Today I will be talking about scaling RayServe from 0 to infinity and back down to 0, which is what the use case actually is. So just 2 sentences about me. Currently, I'm working as a senior data scientist at Outbrain, but this was very recent. It doesn't really matter for this talk. However, I will be talking about my past experience as a machine learning engineer at Heureka Group, which is a company in Central Eastern Europe. They do e-commerce and so on. So let's just get to it. In this talk, I will present a use case and an implementation of a custom serve scaling controller. You will see this is just an if-else statement and nothing else. Just because I promised to my followers on LinkedIn, I will touch a little bit on Ray FinOps, or just how to, just how to think about financials when adopting Ray, because I think that's quite important given how complex the Ray tooling is. And the last part will be my experience with the Ray developer community, which helped us out a lot during these past 2 years that we've been using Ray. So just a little bit of context. We used Ray's ecosystem of libraries and tools as like this central tenet, this central pillar upon which everything stands. And we used it for model inference, so predictions, model training, as well as, and you will see this in the implementation, this kind of provisioning of cloud compute. So this is like one big reason why I personally loved Ray, because you can do this kind of scaling very easily, and by doing that, we can be saving a lot of costs. Just like a quick project overview, what we were doing. So Heureka Group does e-commerce, and there's a few use cases there. These are typical classical e-commerce use cases. One is product classification. So you have information about the product, and you need to put it in some kind of category, just so that you have a nice category, a nice catalog of products presentable and available on your websites. And there's also product matching, which is kind of like product classification, but it's product to product matching. So offers from various merchants. You have offers of various merchants, and you try to match them together under the same product entity, so to speak. So I won't be going into that at all. I just want to more briefly look at, how we used Ray in these use cases. So our goals were basically, when I was starting out as a machine learning engineer, I was just very new to the whole discipline. I don't think machine learning operations was even a word back then. It's being thrown around a lot these days, but I never really found it anywhere on the internet back then. And my biggest concern was just, okay, we're moving to the cloud. We got to keep inference costs as low as possible. So just provisioning a few computes here and there, it was just quite scary to me. And I was really trying not to skyrocket costs at all. So that was my biggest priority. Of course, we wanted to kind of simplify cloud GPU provisioning and management. We were running Ray on Kubernetes, and Kubernetes, it's got a nice primitives for scaling up and down, but it doesn't have primitives for scaling down to 0. In Kubernetes 1.23, there is actually an alpha feature that's basically for the horizontal pod autoscaler, and you can actually query external metrics and see by those metrics you can make a decision whether to scale down the replicas down to 0. So there's like some options outside of Ray for that, but I really haven't seen it at the time. So that's why I wanted to use Ray, just because it looked like we could be doing downscaling all the way down to 0 and spending no money on compute when we don't need it, of course. And of course, I wanted to keep the project code clean, and we had two use cases that you will see, and we wanted to use the same code for both. And by keeping everything under the Ray ecosystem, we wanted to reduce the tooling surface, so that when new people join the company, new people join the team, they wouldn't be having, onboarding that just lasts forever. Those were kind of like a few of my concerns, but there were others as well. So let's get to the implementation right away. I think you can already see this is something very familiar from the Ray documentation. We started out with a Fast API app. It just wrapped up the model and put it to Docker, and it worked for us quite well, actually. I would say we didn't have really any problems with that. It was in production for, I don't know, at least half a year, and it just worked. But then we started thinking, okay, we obviously want to improve this model. We want to take it into the future. We wanted to grow. We saw ourselves using multi-model inference. So we'd have text and images and all sorts of other features that we need to calculate, and have different processor deployments and all of that. All of that was somewhere up there inside our heads. We really wanted to do it, and we wanted to do scaling correctly, because we saw that either our code will get very messy, or I don't know, we'll be spending a lot of cloud compute if we don't really pick the correct tools. So the first thing was, of course, to just wrap our app or our model into a server deployment, and we started from there. So our first use case was on-demand inference. So we were supporting our internal departments for the product classification case, and our models needed to be there serving people from 7 a.m. to 5 p.m. That's roughly 50 hours a week. So it was just a quality of service guarantee. Of course, these models were idle most of the time because humans just don't work as fast as possible. They needed to get predictions. They needed to get suggestions for the product categories. And this is something that just our stakeholders required of us. So we were serving these models from 7 a.m. to 5 p.m. But of course, when you have so much compute being wasted, you're starting to think, okay, maybe we can scale this down a little bit. I mean, can we just spin down the instances while people are not working? That seems reasonable, right? And the second use case was the batch inference jobs. This was for quite a different tool. It's got more to do with automation of classification of products, and there were just some very specific, let's say, architectural constraints. Basically, these batch jobs, they had to fully process all their workloads before the start of the work week. And there was just, let's say, a relatively short window for that, and we just couldn't use the CPUs for that. So the CPUs were just too slow, and that's why we started thinking about GPU instances. Of course, GPUs are very expensive, and so we needed to have the lease time of these GPUs very low, and we just couldn't place this on GPUs, these models on GPUs, and just let them run and waste carbon, just increase our carbon footprint and all of that, right? And we really needed to scale these models down, at least the GPU instances. So we came up with this. Ray Serve uses this Ray Serve API and the Handle API, which we used to control the model deployments themselves. So my model was from the previous slide. And what you can do with this is you can actually just query Ray Serve objects inside serve deployments like normal Python objects. And what we did was we defined a simple controller. You basically make a HTTP put request to an HTTP handle, and what we wanted was to be able to increase the number of replicas for a specific model, which we referred to by the name, and of course specify the number of replicas that we needed, which usually was either 0 or 1, and also whether this model was going to be placed on a regular instance or on an instance with a GPU. And we just let Ray do all the magic of provisioning under the hood, and that would be it. So if this controller got a valid name for a model and said, okay, I want to spin it down, then we just simply called the delete method on the deployment object. If it received something more than that, we just said, okay, we just deploy the model as is, and I think we didn't really need to care whether the model was already deployed or not, because Ray just does everything under the hood. So this is a super low-code solution to model scaling. Why did we need to do this? Because at the time, I think it was early 2021, Ray did not yet include any sort of autoscaling in Surf, and I will get to this. We had a short collaboration with the Ray Surf team. We told them our use case, what we wanted, and so on. But it was, I think there were some issues with the autoscaler back then. So we just developed this, and it was validated by the Surf team, and we just went along with this one. Okay, so what did we gain from this? Okay, as far as on-demand inference goes, we basically achieved a usage reduction factor of 0.3, which means that we were serving the models for 50 hours per week, and also and the rest of the 168 minus 50 hours, those hours were simply, those were the hours that we saved. However, this is not like a huge saving because it's just CPU, right? So okay, so it's not a big saving, but in terms of money, but it is. Okay, and then the second one was these batch inference jobs. If we kept these GPUs up and running all the time, it just wouldn't be financially feasible for us. So we only use them for 30 minutes per model per week. And with this, we achieved a reduction factor of, this 1,000th of what we'd actually spent. And this was like quite a big saving. And this actually was kind of, this was like the big reason why, this was the big result that kind of justified going the Ray Surf way. Okay. Of course, you might be thinking, okay, but people might not be working from 7 to 5 or 9 to 5. Some of them might be working from, I don't know, in early morning, or they're more of an evening working person. And what we actually do is, you notice that the deployment controller was wrapped in an egress, and what we actually did was we used this deployment controller as a router. So every request was evaluated on which model it was supposed to go to. Actually, this if statement is missing, but basically what we do is we just forward these requests to the actual models that were being used. And so this magic right here, what it does is it just gets the handle of the model that we are supposed to use, and these handles are cached, and then just creates another HTTP request to that model instance, and just returns the result back through this deployment controller. And what this does actually is, if the model replica is down to 0, this code actually reinitializes the model deployment through the serve handle API. And unfortunately, this serve handle API is being deprecated. But I think the Ray-serve team is aware that users want this sort of functionality in future versions of Ray. So yeah, kind of hoping that we'd get something similar in the future. So what happens when a user is using the API, they want to get predictions. What happens is on the first prediction, when the server replica is shut out to 0, this code automatically calls it triggers the serve, not the serve, but the Ray cluster autoscaler to request a new pod, and then KubeRay or Ray operator then request resources to be able to get that pod up and running. And if you set the health checks high enough, in a few minutes time, these requests will start being served again. So yeah. So actually going back to this, we still needed to make HTTP requests to this controller, and what we did with that was actually we used a scheduler for that. We just had a cron definition that said, okay, make an HTTP request to this deployment controller at this time with these parameters that we needed for either scaling up or scaling down. And that's pretty much it. So now this solution that you saw is just very low code. Like even what I showed here on the slides, it's not that different from the actual production. However, we have to realize that Ray on Kubernetes, what we were using, actually requires multiple layers of resource managers. And the first one is the Ray cluster autoscaler. Of course, there's also the serve autoscaler, which is a different kind of mechanism, but the Ray cluster autoscaler works on the Ray cluster level, and it just manages serve vectors. Then there's KubeRay or Ray operator, which manages Kubernetes pods and whole Ray cluster resources themselves, as well as you need some kind of resource manager outside of that, which would provision you compute instances. In our case, it was Google Kubernetes Engine, but if you're on AWS or Azure or any other sort of cloud provider, I think Ray has support for that too. Now, all of this is nice because all of the complexity is tucked away under Ray, but this complexity doesn't really go away. You still need to kind of manage it. And so what we found out was that, simple bugs can really throw a wrench into your deliverables. And we faced some bugs that were actually quite frustrating to deal with because we just simply didn't have the expertise to be dealing with deploying Ray clusters ourselves on that level. So I think this level of complexity must be somehow justified. So either you'd have costly hardware, so GPUs or something, or you have deep inference graphs, or you expect the inference graphs to grow as time goes on, or you'd have like a multiplicity of models to serve, so you'd have many models that you need to serve to different stakeholders and customers, and basically the Ray cluster needs to be quite big. It needs to cost a lot for these kind of mechanisms or just deployment in general to be worth it on Ray. So that's just my promise to my LinkedIn followers that I will talk a little bit about this. So it's not all in cloud compute. It's also about managing this complexity. Okay. Now this is like the big reason why I was invited to talk here. It's just my experience with the Ray community. So here's how it goes. This will be just one slide, but if I get too long, just cut me off, please. Okay. So, and of course, you can maybe ask questions maybe in the end if you want. So So my first, the first time I kind of came across Ray was actually for the hyperparameter search library RayTune. We needed to do the hyperparameter search for a few parameters. I don't think it was really justified to really go into RayTune just for those few parameters, but we were evaluating quite large models, slow models, and we wanted to parallelize that somehow. So that's how I got to know the Ray ecosystem. And shortly after, we figured out that actually we want to do multi-model deployments, and we started thinking really hard about scalability. And shortly after that, we decided to put Ray cluster into an on-prem Kubernetes setup. This worked quite well for a lot of time, actually. It was a little bit harder after we started the migration to the cloud. It was a little bit harder to get to know the specifics of our Google Kubernetes engine setup and how Ray would work with that. Like, there's a bunch of different constraints there. For example, security constraints, pod security settings, and so on, that were really not expected, I think, by the Ray team and the documentation. You really needed additional expertise on that, just so that you knew things like, okay, where can I write Ray logs? How can I do that when you can't really, things like that. If you have a strict security context, that means that you need to mount a volume somewhere so that you can write the logs and things like that. So it was kind of challenging just to get Ray up and running because there was no really guidance anywhere. After that, we started talking with the Serve team regarding autoscaling on the Serve level. And what we wanted to do was we wanted to get rid of the controller for scaling and just use something that would be even more low code, and that would be something baked into Serve itself. And we really wanted to use the autoscaler, but as it turns out, the initial autoscaler did not have support for scaling down to 0. I'm not sure about these days. I think it does support that, but I'm not 100% sure. In the end, I think we just kind of ran out of time and we actually didn't use it. But we took a second look at it just before I left the company, and we noticed that it's still not, like, it's quite configurable if you're making HTTP requests and that's all you need, but I think the autoscaler still needs a little bit of work. Like, we opened a feature request for maybe diversifying the metrics upon which the Serve autoscaler does decisions whether to scale down or up or not. And I'm not sure about the status of that, but yeah, there is I would say there is now basic support as we were collaborating with the Serve team. So I think that collaboration was, all in all, quite fruitful, and I learned a lot about Ray, just because that channel of communication was always available to us with Anyscale. So really props for that. And the fourth chapter was there were some dormant memory leaks in the Ray cluster itself, and these were addressed in by various pull requests, not just ours. Not just our raised issues, but other people as well were raising them. And this is actually quite a big topic. I'm not sure if I have time for it, but basically there were some memory leaks related to the dashboard processes, and we wanted to keep the Ray head node on low memory. And what happened was, in 2-3 weeks, the 3 gigabyte or 4 gigabyte memory that we had for the Ray head was simply filled out, and the whole cluster crashed. And because we were routing all the requests through the ingress, which was placed on the Ray head node, the whole functionality just kind of crashed. So this was like a really big saga for us, just because we thought we fixed it, or we thought we made some kind of some kind of I don't know, some kind of roundabout way of fixing it or whatever. And in the end, it turns out actually, no, it's something completely different. And we really had to like iterate. We had these kind of slow iteration cycles so that we finally got to the end of what was actually happening. Anyway, again, thanks for Ray for fixing it. It was like a really tough challenge, I think, for even them. So I'm really glad we sorted that out. And the final one was the Ray 2.0 migration. These fixes for the memory leaks were placed into the Ray 2 branch. And yeah, there was some other introductions there. For example, KubeRay was bumped up to be the recommended way of serving Ray on Kubernetes. And due to our setup, it was really quite challenging to find the time to do the migration. But in the end, we did it. And I think now the Ray cluster, as I left the company, I think it's in really good shape, hopefully. And yeah, that's our experience with Ray. Now, if anyone has any questions, I'm happy. Otherwise, thank you for listening.
Can you guys hear me now?
Yes.
Yes.
Okay. Well, thanks a lot for the questions. Thanks a lot for the presentation. I think I might be able to actually set the context for some of the issues which were actually raised by Miha. So if you guys have any questions, we have the RayServe team on board. Please put your questions on the Q&A panel so we can address them. Now that my mic is working, I might be able to take maybe another 15 or 20 minutes just to give you an overview of Ray, which sort of sets the context, because I was supposed to talk first to set the context of what Miha was going to talk about and what David is going to talk about. So if you guys don't have any questions, I can just jump into my presentation. It'll take me about 15 minutes just to give you a context of what RayServe is all about and what are some of the things that we actually done in 2.0 to mitigate some of the issues that Miha had actually experienced. And then since they have gone on the path of migrating to .x, people will see a huge benefits that we actually have put in Ray 2.0 as that. So I don't see any questions coming on the Q&A, so I'm going to go ahead and share my screen, and I'll present the overview of what the state of RayServe is today, and then we'll get into final, but the most important talk about David. So let me go ahead and share my screen over here. Just give me a minute, and we should start momentarily. Okay, brilliant. This was supposed to be the first slide. This was supposed to be the introduction I was supposed to give, but unfortunately, we had technical problems. So I'm just going to jump into the state of RayServe. We have a couple of announcements I wanted to make. We have a Ray Summit, which is coming up in September 18th through the 19th, and it's going to be in San Francisco, all in person. Those of you who are interested to share your Ray stories, as two of our speakers did talk about, the CFPs are open till March the 6th. It used to be open till February 6th, but not February 17th, but now we extended by a couple of weeks. So go ahead and submit any CFPs that you actually might want. And that's a URL. I'm going to share the slides with the community so you actually have that. But it is open till March the 6th, and we would love to hear about your experiences with Ray in general, and in particular, any use cases you're actually using with respect to RayServe or any of the components that you actually might have. A couple of things that I wanted to mention. We're actually doing a Ray workshop, and this is mainly for people who are in the Bay Area. I know a few of you might have joined us from the Bay Area. This is in person. We're giving a 2-day, 8-hour workshops on Ray about everything you actually want to know about the Ray. Those are the instructors, and if you actually want to join us, it is on May the 11th and the 12th. We call that Ray Saturday, but I think it's going to be Ray Saturday and Sunday. It's going to be loads of fun. So if you're in the Bay Area, feel free to join us. We have done the Ray Saturday before. It was really good success, and we will repeat and double down on that. A couple of meetups are coming up. Few new Ray books are on the publishing already. We have Learning Ray, which is coming out from the original members of the Ray team, and then there's another one from the community by Holden Crow. They're both available for early release on O'Reilly, so have a feel it and go for it. Now I'm just going to go straight into the state of array serve because I was supposed to give this talk to set the context. Okay, here we go. So what I'm going to do is very quickly give you an overview of where we are in respect to array. What are the actual motivations going from 1.x to 2.x? And then double down on a couple of the highlights that we actually talked about. One is the model composition, which has been a new API that actually has been introduced in 2.0, which is in developer review. And some of the auto scaling that we are actually implemented as part of the array serve 2.0, which addresses some of the issues that we actually had before, such as zero scaling and making sure that when traffic is not there, we upscale and scale down. And then the production hardening about what is it for array serve to be deployed in production. And in particular, the focus over here was on Kubernetes and Kubernetes, and that's where most of our users are. So we actually focused on that particular part. Unfortunately, because of the time constraint, I really won't get back into too much of the Kubernetes, but I have 2 talks, and I'll arrange another talk about productionizing Ray serve on Kubernetes. So stay tuned for that. So let me just get into the outline. Those of you who actually have been following the history of Ray from the early days might have heard about the Ray AI runtime. The AI runtime is really our end-to-end toolkit that was announced as part of the Ray 2.0. And it's a unified set of APIs that allow you to build an end-to-end application. And Ray Serve is an integral part of it. And today we want to focus on how we can actually use Ray Serve, the 2.0 APIs, to build an end-to-end inference for Ray. And just to sort of give you a high-level overview, I can use 3 adjectives to actually describe Ray. It's very flexible, it's very scalable, and it's efficient for compute online inference. And what do I mean by that? Now, the fact that Ray Serve is built on top of Ray, we inherently all the scalability benefits that you can actually get from Ray, from scaling a cluster. You get the low latency because of all the network efficiency that we actually have using all the gRPC calls that we actually have. And finally, you get the efficiency straight out of the box because Ray, we continue to make performance improvements, we continue to fix issues, and that sort of gets bubbled up to whatever the applications are built on top of that, which is actually Ray. So the second thing I wanted to concentrate today is on the composition API, which is really, really central to be able to scale and deploy models. Because if you look at machine learning models in general, they don't exist in isolation, they exist in cohesiveness with other models. So I want to double down on that one. And then everybody loves Python, right? We want to make sure that the Ray Serve APIs are Python specific. And today you're going to be building mixing models with your business logic written in Python, along with the latest and greatest machine learning language. So those were the 3 pillars, those were the 3 ingredients that sort of were the motivation behind actually making sure that Ray Serve delivered those. And in order to understand how those manifest itself in Ray Serve, wanted to sort of walk through a couple of applications that are very prevalent and we'll use this particular application as an inference engine. So I wanted to keep that in mind. Now here we actually have an image where you want to feed into some machine learning model, right? Or machine learning functions. And out comes some sort of a structured output that says, what was detected on that particular image? In this case, it's a hummingbird. What was the confidence score that you feel the accuracy is good? And then finally, some sort of pigmentation pixel. So we have a segmentation or a drawing box around the image. So this is a very typical inference engine that you could actually do that. Now, how would this actually manifest itself in? If you were to build that as an end-to-end inference serving in your application. So you probably would have some sort of an application that's actually downloading the image from an S3 bucket or from some data store. You're probably going to feed it to a preprocessor to put some filters in to transform the images, to do some sort of a cropping of the image. And then finally, you might actually have a set of image classifiers that you dispatch to. And then based on the processor output, it might be based on a user ID, it might be based on an SKU, it might be based on a geographic location such as GPU, zip code, or it might be on longitude and latitude. And then in tandem, you actually might want to feed the image process to an image sector that actually sort of does the identification and the object segmentation. And then you want to combine those results into a structured output that you can actually somehow use it. And if you actually were to implement this as an end-to-end application, there are some strict requirements you actually want to make sure that you actually encounter or you fulfill them. One is that you do want to minimize the latency, right? Because latency is going to affect the user experience, and it's going to also affect how the throughput is. So you want to minimize the latency, you want to maximize the throughput so you can handle more queries per second. The second thing is that because you're going to be using both CPUs and GPUs to do some sort of inference into large images, you want to have the ability to somehow use fine-grained resources and allocate fractional resources for those particular hardware accelerators. So that's an important part of the requirement. And then most important, you want to have a programmatic API so then you, as a developer, can actually develop this locally, test it locally, debug it locally, and then easily deploy it in production. That's an important priority because today, most of the people do work on the laptop, and when they're ready, they can actually do the staging and the production. And finally, when you're putting it in production, you actually want to make sure that it actually rock steady. What I mean by rock steady is that it has high availability. It actually has monitoring capabilities. It has ability to update your models or your end-to-end inference service without any downtime. So these are the high table stakes, right? Without those things, it's not possible. And you realize that none of these things that I'm talking about are really part of your ML code, right? This is the technical debt that Google talked about in 2003 when they received the paper of 2013 or 14, when they actually had all these little boxes and the ML code was this little square. This is the technical debt that is not really part of the ML code, but you have to somehow deal with it. And one way to solve this particular problem for our end-to-end inference service that we actually talked about is to somehow use a single container that has all your multiple models, right? So you have your TensorFlow model, you have your PyTorch model, you put it, some Python logic, you stick it together and you put it behind a Flask or a Fast API. And then you develop and you replicate those into a couple of containers, you put in a large container and deploy in Kubernetes. This is a simple solution. It actually works straight out of the box. But pretty soon, sooner or later, you're going to run into problems in latency. Those reasons are because you can't independently take each of these models and then scale them independently. So sooner or later, you won't be able to actually scale those independently. And those problems will manifest itself in high latency and low throughput and becomes costly over time because each of these are different containers you have to manage and you have to upgrade and you have to do that. While this simple solution has been used before, and I'm sure some of you might have encountered and might have actually used it, but it's not very efficient. It has some shortcomings. There might be another solution, right, which is sort of more complex, but mitigates and resolves or addresses some of the issues of the first one, is then to deploy this as microservices. And a lot of people actually do that. So what you do is you have one container that has only your TensorFlow models. You might have another container that has only your XGBoost models, and you might have a third one that has this PyTorch, and you put your Python logic as an orchestrator behind Fast API, and then deploy that in the Kubernetes. Well, this actually works, right? It can scale. If you actually wanted to scale scale your TensorFlow model because more traffic is going over there, you go ahead and create another container. But there are some problems, even though it actually works and you can have independently deploy the resources. The problem is this is quite complicated because now you have bespoke microservices you got to manage, you got to worry. And then think about if you're a data scientist and machine learning who actually wants to deploy those things, you are putting this cognitive burden on them to understand that. And most importantly, is that it does not meet some of the requirements that you actually have to be able to do that. You imagine trying to replicate this particular environment on your laptop can be quite cumbersome. So that is not the best solution. And so you ask your question, Jules, is there a better way to do it, right? And we have an opinionated way of saying this. Yes, you can actually do it. And RayServe is sort of built to address some of the issues to be able to actually use this as a model inference. And the reason you can do that is because we want to make sure that you, as a developer, can write a single Python program that allows you to be able to stitch all these different models together and use your favorite tools, right? You want to use your favorite ML libraries, you want to use your favorite PyData ecosystem libraries to do that. And the important thing is that you should be able to scale any of these models with the appropriate amount of resources, hardware resources that you need across the cluster. And I think this is an important part of it, right? This is an important part of it. So let's revisit our example and how we can actually use these ingredients that we actually have made that part of Array 2.0 or Array Serve 2.0 to ensure that we can actually do this inference example that I referred to. So in that example, we can still actually use Kubernetes as two different separate pods. So you can actually have a one pods, and both these pods are actually managed by Array Serve. And independently for each pod, you can say, okay, for this particular pod, I'm going to use 1 GPU, and for the other pod, I'm going to use 4. And for the second pod, where I might not require GPU, I'm just going to use 2 CPUs. And then independently, and that's an important part because you want to be able to somehow fractionalize, allocate resources for your model. So over here, I can say for my image classifier, I want to use a fraction of the GPU because I don't need to use an entire GPU. I'll just use a fraction of it. And I can just use for the image detector, I don't need it. So this whole idea about being able to write your end-to-end application using a single Python script and being able to scale it flexibly and independently because each of these models can be scaled is actually the part of what we think is the solution to address some of these problems that actually we have. And so the takeaway over here is that with this opinionated solution that we actually propose that addresses some of the challenges that we indicated earlier, single Python script to be able to write the program, you develop locally, you test it locally because all you're writing is Python code. You don't have to worry about IP addresses, you don't have to worry about gRPC calls, you don't have to worry about ingest, you deploy it in a single app. And I think that's sort of the takeaway for this. And just to highlight, we wanted to make sure that for Array 2.0 and an ongoing effort that we're actually making in 2.x is to ensure that we can actually make sure that we can actually use ML in production. And importantly, we're going to give you flexible APIs so you can actually do these model composition in a very friendly and intuitive way. And I think that's an important part because when you start addressing and introducing a lot of friction, you're going to have a lot of friction. And this is a huge problem. The second cost was obviously Miha talked about was auto scaling, right? We have sort of introduced advanced auto scaling as part of the Array Serve so we can actually minimize code. So you're only going to use the models which actually have traffic and you can scale down appropriately. And then finally, we decided to sort of double down on Kubernetes because a large number of people who are actually using Array Serve in production are using Kubernetes. This is not mean to say that we are not addressing those other things, but Kubernetes seems to be a common platform where people actually use that. And so we have created Array Operator for working with Kubernetes. We actually do that and work in conjunction with that. So let's talk about model composition. You know, how do I address this model composition APIs that allow you to use Python to create these topologies as a single graph? And obviously, the requirements are no different from the general requirements of Array Serve. One is we want to make sure that those APIs are flexible. That is to say that you can use different frameworks. And we are sort of in the zeitgeist of machine learning where a lot of people are using different frameworks. So we want to be able to support the latest and the greatest one. We want to combine the business logic with that. And we want to make sure that you can actually develop and debug those locally. I think that's an important part of it because a lot of people actually use their laptop to do most of the development. And then they want to be able to transition over to either staging or production. And then finally, because of the auto scaling, you would actually make sure that whatever you actually produce or what you deploy in production is efficient and scalable. And so our solution is composition APIs that allow you to build this inference graphs, these topologies, which are an ensemble of different actually models as part of the sub-deployment. And you saw Miha talking about how they actually use a particular class to use those sub-deployment as a decorator, and that gets deployed as a single unit deployment using sub-deploy. That's sort of all API. The new APIs, you actually just use that sub-deployment to do sub.run, and then gets actually deployed. And we want to make sure that it's fully flexible and takes the advantage of all the Array efficiencies and facilities they provide. In other words, you can author individual classes as sub-deployments. You can configure them independently to scale appropriately. And the important part is that you can just write it in Python. I think that's an important part. And then one thing good about it is that because it's actually written in Python, you can actually orchestrate all the logic that you actually need to be able to do that. So what do I mean by that? What do I mean by model composition? And I think the thing that we have actually discovered from talking to the community, and even including talking to Miha, was that we saw a few patterns with which how people actually deploy and build actually particular models. One is called pattern chaining, which is an important part of it, where you have certain input that's coming in and you're going to give it to one model. That's going to do some sort of prediction and then takes its output and put it in the second model, and then you finally get the output. This is very common chaining where you're actually doing that. And how we express this in the new composition model API is very quite intuitive, very Pythonic, right? Here we have two models, M1, model V1 and model V2. And this could just be URIs, or this could be just a model sitting on your S3. And you create these instances of this model abstract primitive M1 and M2. And then just using Python code, the context manager, you're going to take the input of first one and you give it to the first particular model, and that's going to produce an output. And you take the model output of the second one and you forward it to the second model, and that gives you the output. Very simple Pythonic API. You don't have to worry about ingest. You just do that very easily with using these composition primitives to do a chaining of a bunch of particular models. And this is a very common use case where people will chain things together, whether you're actually doing transformation, whether you're doing pre-processing, whether you're actually applying some sort of a business logic where you're looking at a particular feature in, say, a feature store and combine it together to the output and then give it to the next model. So this is no different. And then finally, there is the ensemble pattern where you actually have an input where you broadcast it to multiple models, and then each will produce a particular output, which is then somehow combined to a combiner. And the combiner could just be a business logic or a class that you actually write, and that's going to produce the final output. And this can be expressed quite equally and quite intuitively with this particular composite API. Not very dissimilar to the previous one. We actually create model 1, model 2. And over here, we just and wrap that into a Python orchestrate engine where we send inputs to both the particular models, and then the output of those can actually go to the combine, and then combine will combine those two outputs and then produce the final result. And last but not least, and this is a very very important pattern. It's called a dynamic selection, where you take the input and you broadcast it to multiple models that you actually have. And then based on certain input criteria, it could be a user ID, it could be a geographical location, it could be longitude, latitude, it could be a color, whatever you want to have the particular criteria. This particular dynamic selector will choose the particular model, will use that, and then create the final output. It's not both output, it's one or the other. And then over here, same logic, very simple to express yourself, the topology, you actually have those two models. And instead of sending the output, what you're going to do is you're going to send the models to this particular selector. And then in the orchestration, you're going to forward the input to both the dynamic selector, and it will actually decide based on the input which model to use for prediction, and you'll get the final dynamic output. So I talked about these patterns over here. How do we actually apply to the application that we have been talking about, which is the understanding of our inference engine? So over here, if you were to take this particular patterns, you'll see that they can be used quite easily over here. So for my chaining, I would actually use my downloader and preprocessor chain together. For dynamic selection, actually, I would use any of the three classifiers that I actually have. And in tandem, I can use ensemble with my dynamic dispatch and my image detector. And then the output of that could be given to a combiner, and I get my structured output. So that's sort of quite an easy way to build this particular model as an end-to-end application using this model composite and API. And this is just not one single model. This could be a multiple actually models that you actually create a topology of that. So just overview, Ray Composite and API allows you to write very simple ordinary Python classes that you can actually do that. And this is part of the Ray 2.x. Currently is in developer preview, but we're getting a lot of feedback. A lot of people actually using it, and they just love the patterns that allows them to do that. It flexibly has the ability to actually compose those models. And you can actually see, you can actually mix both your ML model code as well as your business logic in Python code. And then finally, you can run and test these because they're written a single Python script. You can do it on your laptop. And more importantly is when you want to deploy into production, you can independently scale these models independently. I think that's an imperative for array serve to be able to take these model composition have and individual models and compose them and then scale them independently and allocate appropriate resources to those when it's actually needed. Now, talking about scaling, what does it actually mean to scale in the new world that we actually have introduced into that X? Now, one of the problems that auto scaling will have to address is because model machine learnings are expensive, they're very compute intensive, they take a lot of resources. You have to make sure that the models are used efficiently to actually save the cost. And so not all the models are going to be used at the same time. So if you have a large cluster and you have a lot of models you have deployed, at some point, you might have a very skewed traffic only going to certain models. And those could be auto-scale automatically. But what are the other ones which are not being used? So somehow you want to bring them down, and that way they don't take the resources. That's an important part. That's an important table stakeholder. Some of these models can actually be hard to use appropriate tuning for hardware utilization. You might have to profile them. You might have to make sure that you actually do some sort of vector prediction. So those are problems hard to solve. And then they have to work with multimodal. That's an important part that actually works with multimodal. And we believe that the advanced auto-scaling for array serve, which we introduced in 2.x, actually helps a lot because it addresses some of the issues that Miha talked about, which is how do I actually scale it down to zero? Because I have these models which are sitting there and they're not being used. I don't want to use my hardware resources. I want to be able to actually reschedule the resources everywhere. So we want to be able to scale them down to zero. And that's an important part of it. And then I don't want to go through the profiling and I don't want to go through optimizing my particular code. Why don't we just use some type of heuristic where I say, if I start getting my request queuing up for a long time, I want to be able to use the profile. I want to be able to auto scale or put some more replicas on the fly. And then finally, this has to be completely compatible with my composite API. They have to work in conjunction. So how does it actually work with our application? Let's go back to the inference application we were talking about. Over a period of time, you realize that all the queues are now being directed to the image classifier number one, and maybe some of the images are going to classifier two. And all of a sudden, now we begin to actually see the latency because of the fact that the image classifier is the only one that's servicing this large backlog of queue. So what the autoscaler will actually do with respect to RACO is that it will look at the particular input request coming in from the queue and it says that, oh, my queue size is really huge. So I'm going to go ahead and replicate my image classifier and create 3 different instances of those, and I'll redistribute the load over a period of time. So what we have done is you've auto-scaled that to minimize minimize the latency, and it can get sort of more of a high throughput. So now you have 4 instances or 4 replicas of image classifier, which are now serving those particular requests in tandem. And this is automatically done for you. You don't have to worry about it. And the second thing you might actually notice that there's no request going to image classifier 3. So what do we do at this point? Over a period of time, over certain minutes configurable, we can remove that particular replica, which is coming down to what Miha was talking about, scaling down to 0, because you have a model sitting there and occupying your hardware resources. You want to scale it down to 0. So that's how sort of the auto scaling actually works. And it's actually really quite simple. You don't have to sort of think about writing a manifest. You don't have to worry about, mucking around with Kubernetes. All you do is in your server deployment in the new API decorator, you provide the auto scaling config saying, these are the minimum replicas I want to scale it down to 0. The maximum replicas I'm on is 10 if the queue size is very good. And then these are the number of the size of the queues. If I have anything more than 2, I want to start thinking about auto scaling. So that's in a nutshell what the auto scaling is. Now, because of the time constraint, I want to give my esteemed colleague David to give a talk. I'm gonna create another talk that talks about how we actually have doubled down on Kubernetes, because we have to make sure that we take the advantage of RACE. So its flexibility, its user experience that I talked about in terms of doing composition APIs, and the efficiency comes naturally because of the RACE. And combine that with the operational benefits you actually get from Kubernetes to see how you can actually use in RACE in production. And this is going to be a separate talk. But if you're curious to know exactly how we actually have done that, there is an in-depth talk about high availability architecture for online serve on the Ray Summit, you actually go to that particular Ray Summit page. Operationalizing Ray Summit Kubernetes is another good talk. And those are the talks that we can actually recommend now. Because of time constraints, I can't get into it, but we'll arrange one particular talk. And there's another couple of talks that you actually might be interested, where the community talked about how they're actually scaling Ray Serve using the zero copy model, using the object store, because now you can actually do a zero copy, because the models can actually be stored on an object store. And if you have a model which is deployed on the same node where the object store, we can actually just do a zero copy from the Ray store. And then another company called DeepSet, they actually implemented RayServe as part of the question answering, so using some of the NLP, which we're going to have the next talk. David talk about that. So you guys are welcome to do that, but stay tuned for a more in-depth version of RayServe on Kubernetes coming up soon. So with that, I'm going to just recap. As I said, well, our goal was to make sure that ML in production is easier with RayServe. We do that by making sure that the user experience for the developer is quite easy and intuitive, using the flexible composition APIs for you to be able to build these topologies and then use them in one single Python script. I talked about how we can actually auto scale independently any of those particular models and have a fine-grained use of the hardware resources. And this is actually done quite efficiently and automatically. You don't have to worry about that, just through those configuration parameters, and then productionizing and hardening on Kubernetes as the best way, or one of the ways to do that. So if you have any questions, let me know, and I'm going to stop sharing my screen. I don't see any questions. If not, we'll have David, our last speaker, talk about Argila and how they actually use RayServe over there. Go ahead, David. It's all yours.
Yeah, thanks for the introduction. So I'm David. I'm a developer advocate engineer at Argila. And I'm going to talk about shortcuts for bootstrapping NLP pipelines before actually being able to serve them with RayServe. Where I'll be going a bit more into depth on how you could potentially use Ray data to actually distribute data processing for pre-processing for NLP, and also give a brief overview of using like Ray Train and Ray Tune to actually create a model for a arbitrary NLP task. So this is the agenda for today. Initially, we'll start with a very brief into NLP. Then eventually I'll give an intro about Argila, what we do. I'll get back to you with these cool shortcuts, weak supervision, future learning, and active learning. And eventually we'll wrap up. So a brief intro into NLP. Initially, if you said that you did something with text and AI, everyone's like, okay, cool. But now with ChatGPT, I can actually explain it to my friends, and they are like, oh, cool, you're doing something with like these cool AI models. So that's nice. What I'll be focusing on this talk is actually a use case where we'll like bootstrap a text classification model from scratch. So you have a bare data set without any labels, and how to work towards a data set that you can actually train with these smart shortcuts for actually labeling data. Another good thing to notice is the difference between lexical and semantic similarity within text, where lexical similarity is really focused on exact keyword matches, and the semantic similarity is more conceptual equality. Like if you talk about football, sports, and soccer, they aren't the exact lexical same words, but they do kind of coincide in the same conceptual meaning space for humans. So Argila, what do? We are actually an open source labeling platform for data-centric NLP, and what we mean by that is actually that we want to focus on high quality training data instead of like having these big, huge data sets that maybe also contain this less structured and less organized data, because we actually believe that if you improve these models over time, that you can eventually get way better results. And we do that by actually allowing like both data scientists, ML engineers, and just human experts to be able to work with these data sets and work with the Argila ecosystem. So Argila has like three main components, and on the left-hand side you actually see the Argila Python client along with potential models that you might want to use to bootstrap your project. because there are like a lot of open source models out there and a lot of open source data sets and benchmarks data sets. And to get started with model, you probably want to use some of them to initially load your data into Argilla and then log it into the server. This Argilla server actually stores and manages the data sets and computes some metrics in terms of like the accuracy and the text length and some other text specific metrics before logging the data into Elasticsearch, which is like the database backend against which you can query and nowadays also do these semantic search queries based on KNN similarity. Jules already mentioned DeepSet, and they have also this cool ecosystem to do the semantic search and vector search based on text similarity instead of just focusing on this lexical keyword similarity. And since a couple of years, Google has also introduced these kind of things into their Google search engine. So that's pretty cool. And then finally, what you can do within the Argilla UI as a non-technical user is actually level data, traverse data, filter, query, everything you might want to do to actually get to know your data instead of just passing through records and records and records, which might be boring and less intuitive. So for us, it's really about getting to know your data and getting a high quality data and iterating over time. Within Argilla, we've got like users and workspaces, so you can either work together or as a team. And this is kind of what it looks like, where you have your dataset name, the workspace assigned to either a specific user or a group, and then the specific tasks. For now, we will focus on text classification, but you can also focus on like token classification, NER, named entity recognition, where you might want to extract specific persons or locations or other entities from text, and text generations or text to text. We also like working a lot with the community, so like these ways in which ChatGPT-3 is trained with reinforcement learning human feedback. We're also looking for ways to actually integrate that within our default task and default workflows, because a lot of users have of course been asking for that. Normally what we see as a default training workflow is that you really start with a bare empty data source. You want to like read that data source, create records within Argilla, and potentially infer some model or heuristics so that you have some initial predictions. These predictions are not going to be good, but it's really about bootstrapping and getting some initial estimations for your predictions. Eventually, then, if you look at the UI, you will like traverse the data, explore and label the data. After that, you'll need to like load the records, prepare for training, and actually train with your favorite NLP framework, which might be Transformers, Spacey, Spark NLP. And we actually have some integrated methods to directly export our data via one API call within Python to be able to use it directly for training. And then you don't need to worry about this data formatting stuff. That's really annoying because we've handled that for you. And then once you have your trained model, what you can do is like monitor these model requests. Maybe you're like hosting it within Reserve and actually use like SG middleware or monitoring or async logging, so as to not block the actual inference time, to monitor and log these predictions into Argilla again. Because eventually, if you're a model, you will want to keep on monitoring and improving on the data. For example, ChatGPT didn't exist a year ago. Nowadays, it's a cool hip thing. So you will actually need to retrain your model to pick up on these kind of words as well, similar to COVID, maybe other things that might have happened in the recent years. And these kind of data shifts, data drift thingies that tend to happen. You'll want to like keep track of your data set, improve it, and keep it high quality as well. And once you've like labeled and explored your data, we've got some built-in metrics like one score and accuracy, and you can actually load your records again and prepare for training, train a new model, and that's kind of how we close the MLOps loop. So these are some like snapshots from the Python client, where you can see that's relatively straightforward to create a record. In this case, a text classification record with predictions and prediction and annotation, where initially you make an assumption of what a model, what the label might be given a score, and then eventually there's one golden standard label that you actually assign, which is called the annotation. We also provide like these operations for loading data from and to pandas, and to actually log these records relatively easily, where you have like a created record or a list of records that you then log into the data set. Similarly, for loading, you can actually pass a query where you and a dataset name, and then eventually actually call the prepare for training method. And this is like a default universal prepare for training for transformers. So for the like major NLP framework. For this use case, I will actually be covering like a dataset which we host on the Hugging Face Hub, which is like a model data set, and nowadays also a UI library where you can really easily get like these transformer models, BERT, text-to-text, text classification, and nowadays also image support and computer vision support. And for this, we will focus on the task of classifying each of the input entries to either science or tech, business, sports, or world. And this is actually a snapshot of how to load data from the Hugging Face Hub, and actually quite easily within 3 lines of code load it into Argilla, so that you can actually get started with labeling and creating your high quality data set. Normally, when you actually like upload your data into Argilla, there's some ways in which you can explore within the UI. You have got like the keyword search bar that you can see on the right hand side. There's these built-in text queries for which use the Lucene query language. They have some default operators like and or. Wildcard queries are supported, and also these regex queries. And we've also got filters built in to either filter on metadata, like some custom metadata that you add, and some actual data that we add by default, like the annotated as, or some less updated timestamps and these kind of things. And underneath, you can actually see a record here that is actually matched by the filter politics and president. And you can see the highlighted words, the assigned label, and these kind of things. Another thing that you can do is actually add highlighted text, so that during like this labeling process, annotators might be more nudged towards looking at the specific nouns, so that during the annotation, for text classification, you're more inclined to look at like the word gains, euro, economy, dollar, euro, and then it's a bit more easy to actually start labeling and go from the bare minimum blank data set to a high quality data set. And another cool thing, what we've where we've added support for is like this similarity search based on vector embeddings, where if like input text is similar, then the embedding or the embedding present in the embedding space is also going to be similar. Where with the example again with football, soccer, and these words, they'll end up in the same space within the vector space, and that these records can actually be created by the example on the right. So if you actually go into a brief demo of like how to query Argilla. You can actually see like the query about politics and president. And what you can, for example, also do is politics for president. And the nice thing is that when you actually have these hits for the queries, you can actually see these keywords updates on the side as well. So for politics and president, there are going to be a lot more records. So the keywords actually update. So this means that you also are aware of what data might be in your query, or it might be hit by your query. Additionally, what you can do is like filter on predictions or filter on annotations, the metadata I mentioned, the status of it being either validated or not. And similarly, what's cool is that you have this find similar button, which really covers the semantic search part of everything. And as you can see, this is a record, and then eventually end up with the most similar records. And these are all world all these records cover world topics. So what you can do is actually select them and all annotate them as a specific example. So by doing like these filtering, querying, and these kind of things, you can really like traverse your data set a lot quicker than you would normally do. what you want to do before you actually need to, before you actually have the capability to do semantic search, is actually do these inference loops, where you want to have your data set, you want to upload it into Argilla. And for doing that, I actually played around a bit with rate data to do like this distributed pre-processing, where you initialize the sentence transformer model, in this case a very default one, and actually distribute the data over these 4 actors, or 2 to 4 actors that you might want to autoscale to. And you actually assign a number of resources that each one of these actors can use. And due to the fact that like these models are actually quite these models can be quite large language models, you actually distribute the task load over your cluster, and therefore it can be done more easily than you would do it like individually. And recently, a user as one of our users was quite active in Slack that also had the same issue, where he wanted to embed, I think, vectors for 30 million records, and use this similar use case along with a package that actually transforms the sentence transformer model in a Onyx representation, so that you actually dial down like the model memory, and also this increase the speed by doing that. I actually have a package for this made myself, and I will also forward the references to that later on. So then we will actually get to the first shortcut, which is weak supervision, where you actually have this raw data set and intuitively start to query the data set and define rules based on these queries. Where, for example, you have these query that we had with politics and president, and then eventually assign a label to that specific query if the records hit or match that query. Then you end up with a weak labeling set, and you actually compose a label model, where this is like a decision tree kind of. If a rule matches a query, then you actually assign a label. And then you can use this labeling model to actually train a data set as well. So you end up querying Argilla, choose relevant keywords based on the keyword sidebar, define rules that are human readable, quick and easy, and even no programming knowledge is required. Even though you can also on the right hand side see that you can actually define these rules programmatically as well. So if you have like a knowledge base on the side, which on default key terminology that you expect to see in certain records or for certain labels, you can actually choose to include those. And what happens is that you actually can directly export this label model and actually apply it to a data set and prepare the data set for training. And then you end up having like a default like model, which you can use for training a transformer model that is a bit more like a bit more robust. And then you have like a decent baseline to get started. So within the UI, you can also like verify these rules. Where like this rule would, for example, be the word minister. If the word minister occurs within one of these records, as you can see, I want to assign the label word to it. You can actually see for each one of the rules that you define what the coverage is for the rules. So how many of the actual records are present, how many records it hits from all the records that are present, and you can see how many of the annotated records it hits. So for now, I only annotated 32 records. So 2 out of 32 actually have a match. And out of those 2 are correct. So for this rule, you actually know that the precision given the annotated data is 100%. And then you end up like with an entire rule set that a human can actually interpret, and you can also verify against the annotated data. And you can actually use to train a classifier. Another weak supervision approach that I was playing around with is actually based on these vectors that we obtained via the array data integration. So if you have your data set with all these vectors, what you can do is actually load the annotated samples and actually average out the embeddings of these samples into semantic exemplars, as you might say, where, for example, within the blue cluster, you would end up with like grabbing 8 of the annotated examples within the blue cluster, averaging them out, and then from the average, look at the most similar records and actually apply predictions based on that, given the assumption that like things are going to be semantically similar, so they're going to be semantically equal, semantically in the same space within the vector space. You might use that to actually apply predictions. And by doing this, you actually have these like pre-computed embeddings. You don't need to train any classifier, and you can safely assume that when you have these annotations already set up, you can relatively easily make these predictions that the most similar records are also going to be records of the same class within text classification. Then another example of a cool shortcut to get your data set from no annotated data to decently annotated data is few-shot learning, where you'll have like these couple of examples per labeled class and actually start your training process with these couple of examples. In my case, as you might have seen within the UI, we ended up starting with 8 annotated examples per class. And these annotated examples we actually use for a package that I created, which is classy classification, which uses like spacey or sentence transformers embeddings and support vector classifier to actually train a classifier from scratch and use a Onyx model representation to also make the inference a lot faster. Because normally if you like need to train a custom bird model or any other transformer, you'll end up needing like thousands of examples and GPU to actually train it. But this is actually done on CPU, and the training and inference for like 500 samples within the data set just to get the most certain samples runs within under 1 minute. And on the right hand side, you can actually see some code that like loads the data from Argilla for all of the records that are validated. Creates a training data set for classy classification, and then eventually assigns it does like inference for annotated data and updates that data specifically within the data set. And that's also another way to get from like 8 examples per class to like 500 labeled examples, based on some heuristics and assumptions. And a bonus is that you can actually use like multilingual models as well, which ends up giving you multilingual predictions, where, for example, low research languages might not always have data available, and you might want to like move from one of your like English data sets to a Dutch data set. And this is also an approach that I used for another package, cross-lingual coreference, that I made at my previous employer, where coreferences are resolved within NLP. Finally, there's active learning, where you really focus on side-by-side learning and of a human and a machine learning algorithm or AI, where initially you, as the Oracle start labeling data. You have your labeled data on the right, which you like pass to a learner. That learner actually evaluates the unlabeled data, and the unlabeled data actually gets either filtered or selected based on the certainty of the predictions, for example. So if like this few-shot learner actually picks up on predictions that are very certain, you might make the assumption that they are correct. And then you can, as an annotator, actually give preference to looking at these more certain predictions to make the annotation process go a bit more smoother. What the nice thing is from classic classification or the few-shot learning approach I just showed you is that it actually can run quite fast and side by side on CPU. So normally for like doing active learning with birds or the small text package, you will end up needing a GPU, and still it takes some time to actually process the newly labeled data and to do one like training step. But with the classic classification, you can actually do that side by side. So you can actually work smarter, listen to newly annotated examples, so the most recent annotated examples, update your model, and then make new predictions. And we actually wrapped around this like workflow within like a more easy interpretation, where you just import classy classification as an active learner plugin, then direct it to a specific data set within Argilla, and actually start the plugin. And then in the background, it actually starts labeling. And that's also a brief demo that I wanted to show. So here you'll end up with importing the class learner. The class learner is for the dataset race summit, the execution interval by which it's going to check the dataset for newly annotated examples in the background is 1, and the batch size by which it's going to make predictions is 10. So there are some variables that you might configure, but in the end, it's also going to be a lot easier than coming up with all these assumptions yourself. So what happens now is that it actually starts like this background process. And due to the assumption that I made that we want at least 8 samples per class, it now states that we don't have enough samples. So if we were to go back to like the UI, you end up with labeling this as sports as an annotation. And then what is going to happen is actually classification. So the active learner is actually going to load the data and in the background log new predictions into Argilla. Going back to Argilla, if you go to sorting, then go to last updated, most recent. What happens is that you can actually see like these most recent predictions with a prediction score. And this will really help when you are annotating and going over the newly annotated records. These records and these predictions are going to be more certain. And it's relatively easy to kind of say, okay, this is correct, this is incorrect. And it will improve over time, and you'll like do the active learning workflow side by side while also improving your model. Then eventually, so when you've got all these applied all these cool shortcuts for bootstrapping NLP pipeline, you can start training a formal model. And I actually created some code snippets to showcase how this would be done via integrating both Ray Tune and Argilla, where you initially on the left-hand side would like load some data from Argilla, prepare that data for training, and then on the right-hand side actually use Ray Tune for hyperparameter optimization. And eventually you might also use like a Ray Train to do distributed to set up a distributed training process if the data is turns out to be too large, or if you just want to speed up your training process. And the nice thing is that this approach also directly integrates with weights and biases, so that you can actually directly see like the output of the training processes, where like and for all of the runs that you did. And similarly, a thing that I do really like is that nowadays they've also got like this system GPU, what usage and these kind of things, because this has been really discussed for like these larger language models, what the sustainability impact might be for these kind of things. So to wrap up, what I generally like to do is think about the resources that you do have. So for like these weak supervision rules, you end up with some rules that the human annotators are aware of. Be creative and iterate over your data. And that's kind of what I recommend doing for these NLP approaches where you don't have any data and you really want to get started and bootstrap your process before starting to iterate over your data and your data set. Then eventually this is a use case about, this is an example of like the package I mentioned before, cross-lingual co-reference, where there wasn't any data available in Dutch. I'm from the Netherlands. And we actually needed to get a a co-reference model up and running in Dutch. And we actually decided to use a cross-lingual model as a default model to train, but using our English data set. And eventually it also proved to work on like Dutch, German, French. And nowadays it's, I think, one of the only models that's like multilingually available for co-reference resolution. So that's pretty cool. And this is another example where I found a cool way to work on like a few shot entity recognition, where you have like these labels and only a couple of examples. And you really want to get from having no label data for entity recognition to some default data to get you started and to actually iterate and work towards a decent data set and training a model and eventually serving it, of course, with RayServe. These are some sources that I use. So Argilla, REPL, we have some cool data sets on the hub. Nowadays, we also have the option to actually deploy Argilla along with Elasticsearch and some test training data sets within within Hugging Face spaces. Something about B, the packages I created can be found under Pandora Intelligence. I do some volunteering as well. And some other packages that are cool for few learning is SetFit, Weak Supervision, SK Week, and active learning, small text. And that's it.
Thank you, David, for that broad introduction to the NLP use cases. couple of curious questions. I saw you actually use Ray data. Excuse me, losing my voice.
Mm-hmm. No problem.
To do your batch training, so you're actually using Raycore's active pool strategy to create minimal number of actors and maximum number of actors. Mm-hmm. What did you see the benefits in there? I mean, why did you choose to do that compared to, say, something else? Was it something that gave you the ease with which you could actually train and distribute your data using the Raycore strategy? Or
that was like the easy out of the box availability, because otherwise you will need to send up something like host different models separate, or like you could use RayServe, for example, but then you would need to handle all these logic in terms of making requests and these kind of things if you want to be able to scale this automatically. And now you can use the easy like Python API while still using like pandas and things that I at least intuitively I'm more familiar with. And similarly, this like pipeline that you set up also works for like only using one data set, and that's only using one model, or just using it locally.
So for the Ray tunes hyperparameter tuning, I mean, did you take an existing transformer Hugging Face model and fine tuned it to do that? And this was what the text classification model.
Yeah, exactly. So for the model, I actually used a tiny bird model because the demo purposes. So it used a tiny bird model, which you can quite easily test and train on a local device, or a bit more easier than a default bird model. But yeah, you can plug and play any arbitrary model that you want. So in Hugging Face, as I mentioned, you have all these default language models that you can just call via using a string.
Yeah, as a matter of fact, I don't know if you're actually aware in our Ray API of the Ray train, we actually have added the Ray trainer for Hugging Face. You can actually take any Hugging Face and wrap it around your PyTorch trainer and then do the tuning. Did you actually use that API, or you just use the Ray train itself?
Yeah, I used the Ray tune initially, and then eventually I wanted to use the Hugging Face trainer.
Hugging Face trainer,
I got this CUDA error, which was which I wasn't able to resolve in like easy short time. But it might be something with Apple Silicon.
Yeah, I think it would be sort of a good addition, because we're actually really quite doubling down on making sure that people are actually using quite a bit of Hugging Face trainer by just, as you said, providing the pre-trained model, and then we actually tune it to do the specific task, where they're doing summarization, where they were doing entity, and then using the Ray trainer model on top of PyTorch allows you actually to scale quite a bit. What I was curious was when you were actually doing this NLP inferences, did you actually use RayServe of any of the APIs to deploy the model using some of the things I talked about earlier, or was it something that's still under investigation?
No, still under investigation. So for now, I've at Argilla not actively used RayServe. At my previous company, we did. So we had like all kinds of models for English, French, Spanish, and Dutch. And then, for some clients, the certain models were used more often, and then we would use it for these kind of use cases. For now, I was also thinking for RayServe, potentially looking into it to, for example, host these active learners, scaling to 0, and whenever someone like starts an active learning loop, that you could potentially like boot up the active learner, make sure that the inference can be done in terms of the embedding that you might want to do. So I wanted to play around with that a bit more. But yeah, for now the plugins is like a toy use case, and we are like looking into how we can extend that there. I've been working with Phi, for example, your colleague, to look into like the ASCII middleware integration that we offer to actually also monitor these serve models, and actually make sure that all of the predictions from each one of these models actually come into Argilla correctly, so that you don't lose any of the valuable data or predictions that you might have done.
Yeah, I mean, we certainly would be interested to see how actually Argilla can actually use RayServe at scale, especially some of the things that you're actually doing and some of the use cases that you talked about. And I think it lends itself very easily to some of the scaling that you actually talked about, and I think some of the issues that Miha ran into. Miha, question for you: did you feel the 2.0 APIs for model composition and the problem that you actually ran at an earlier company? And I think it was you actually started the initiation by filing an issue in PR saying we actually want to do zero scaling. So we did implement scaling down to zero.
Yeah, thanks. Yeah, actually, I remember what it was, why we haven't gone through with the autoscaler for Surf. It was like a combination of time and just other, priorities. But also there was, like, I think this is a big issue for serving RayServe on Kubernetes, is that we were like, one key element of making RayServe work on Kubernetes is the fact that we needed to optimize our Ray Docker images. And we already did, actually. We split them up into GPU and CPU and stripped down a lot of libraries, but there was more work to be done. And the problem was at the beginning, when we started, we had quite a slow connection between the Docker repository and the Kubernetes cluster. And this took several minutes, actually around 5 minutes when we first did it, to actually download the Docker image to the pod, start it up, bootstrap the pod, and then also load the models, which transfer the model from, let's say, a bucket, and then load it. That the last part took just a few seconds still, but all of this was I would say quite a bottleneck when it came to quickly provisioning pods for autoscaling, for this kind of fast dynamic autoscaling, and those tasks needed to be done first, I think. We also were on Onyx, and we tried, like, I already had stories written out, we just couldn't get to it.
Yeah, so I mean, we like I said, I think the continuing effort, and Akshay, who is the engineering manager of RayServe, will attest to that. They've been putting a lot of effort in making sure that the doubling down on production for RayServe, especially the Ray operator that we have actually specifically built on top of KubeRay, to be able to very seamlessly and easily update, scale the new RayServe application. You actually don't have to worry about writing a manifest. You just use the serve command that we actually have. You take your entire Python application, you give it to serve to actually go ahead and build, and it actually builds a manifest. And then you can actually use kubectl to deploy that manifest, and it will actually deploy it through the Ray operator to the KubeRay to go ahead and update, create a new cluster, and update in replicas. So if you wanted to change your configuration, there's almost zero time. So look into that, and I think you actually might see that it addresses some of the questions. Yes, David, you have your hand raised. Go ahead.
Yeah. So, but I was curious what your view, because now you're mostly talking about scaling up and down. But what is your view on making sure that these models are as efficient as possible, like either using sparsification, Onyx, these kind of things, quantization.
I mean, obviously the quantization, like I said, remember when you're thinking about a model, efficiency, there are two ways to do that. One is either to profile the model, or you actually quantize the model to break it down into all these different smaller parts, in where you can actually do the prediction easily by quantizing that. I think all that work is actually going on to be able to do that, especially when you're dealing with large models, right? When you're dealing with large ML models, some of them don't fit in the memory, so you have to break it down. You have to actually make sure. So all these efforts are on our roadmap. Is anything else you, Akshat or Sihan, you want to talk about in terms of our efforts for quantization? But I'm not sure about Onyx yet. I don't know if that's on the roadmap. Can either of you speak to it?
So not really too much for model itself. We still rely on any third-party library to optimizing your model. And on the server side, we are supporting any hardware acceleration. For example, if you want to go for Triton for your GPU, or you want to go to more deeper, or using the inferential on the AWS side. So I think both of this can be supported on the reserve side. But on the model itself, if you want to use Onyx or using any third-party library or DeepSeek to directly optimize your model, that totally fully rely on the client side or engineer to do any magic there. Yeah.
But David, you raised an interesting question. I mean, in terms of the quantization of what sort of, whether you want to use FP16 or whether you want to scale it down to an integer, I think that also depends on the PyTorch underlying model. So when you actually send it to a particular CUDA device, you can actually specify, how you actually want to quantize that. So I think that is not so much part of the RACER itself, but it's sort of more part of the underlying implementation of PyTorch.
But it was more like
general
landscape question.
So like I said, the quantization bit about breaking into or making sure that the inference is quite. Those are the techniques that the underlying framework actually gives you, and we can sort of your Python code is just going to say, okay, I'm using a CUDA device and I'm going to quantize that and scale it down to FP16. So those are the things which are sort of more library dependent. Any other questions? I think we are coming close to almost there. I do want to thank David. I do want to thank Miha, and I do want to put in what I really want from both of you is that if you can actually send me your PDF versions of your slides, so I can make it available to people who actually couldn't attend. So thank you very much, and have a good evening.
You too. Okay.
Yeah.
Bye-bye.
Thanks for the opportunity. Bye.
Thanks for the invite.